All right, here we are, chapter 12. You ready to go, Fred?
Yeah, I'm ready.
All right. So as we kind of talked a little bit about at the beginning of last chapter, intermolecular interactions, which means interactions between molecules. So for example, if I have a molecule of ammonia, that was the one we chose last time, and I'll draw it out because I'm very good at drawing Lewis dot structures now, right? There we go. There's ammonia. It has a little bit of stickiness with a neighboring ammonia molecule. Now, why does it stick a little bit? Do you remember, Fred?
It had something to do with the polarity, but I can't remember right now.
Yeah, has to do with the polarity. It had to do with that little thing right there. What does that mean?
Oh, that's the partial negative charge.
That's right. And there's a partial positive charge right there. And so a neighboring molecule, and that's what we call these, intermolecular, which means between molecules. A neighboring molecule will have a delta minus partial negative charge here and a partial positive charge here, and that will result in some interaction between this slightly positive end of one molecule and slightly negative end of another molecule. Okay? And this stickiness governs the melting point or the boiling point, right? The point at which gaseous molecules, when they collide, will stick together, right? That's the energy necessary to separate that is the boiling point, right? To separate liquids into gases. And these are the intermolecular interactions that we're going to, intermolecular interactions or intermolecular attractions that we're going to talk about in this chapter here. Now, the reason why this partial negative and partial positive charge exist here is because nitrogen was much more electronegative, right? And this is a chart of electronegativity.
Are we going to have to remember all those numbers?
No, we don't have to remember the numbers. We just have to remember that nitrogen, oxygen, and fluorine are the three electronegative hogs that pull electron density the hardest, and that they increase in that order. Nitrogen is above everything else on the periodic table here, and fluorine is above oxygen, which is above nitrogen. Okay? If we remember that much, then it allows us to identify polar bonds, and then thus polar molecules, and then from that we can begin to think about what we call these intermolecular interactions. Okay? We call a polar bond, we say that a polar bond has what we call a dipole. And using those numbers, and some other calculations as well, using these numbers, we can actually calculate what we call dipole moments on bonds or on molecules. All right? Now, we're not going to actually do those numbers and talk about dipole values, but it is these dipoles that result in molecules interacting with neighboring molecules that are the same as them. All right? And so we call this kind of an interaction between dipoles, where one molecule has a dipole and another molecule has a dipole, and then we have an interaction between them. We call these interactions Fred.
What?
That's the name of the interactions. We call them Fred.
You call him Fred?
No, I'm just kidding. I was just seeing if you were listening. We don't call them by some crazy name. We call them dipole interactions because one dipole is interacting with another dipole. Okay?
Why'd you say you called him Fred?
Well, I'm just trying to make sure you're paying attention. And I want you to also recognize that the name of the type of interaction is showing us the kind of interactions that are kind of molecules. One molecule has a dipole, the other one has a dipole. That's why we call it a dipole-dipole interaction. So for the if you have the type of intermolecular, the type of molecular bond that is here, or in this case it's a dipole, then you can know what kind of interaction results, what kind of intermolecular interaction there is. All right, molecules, just like bonds, so this is a molecule, HF, but it's also just a single bond, right? Molecules, and this is again a review, are polar or nonpolar based on whether or not they have these polar bonds in them. But there's also something else. Do you remember what it is?
They need to be asymmetrical, right?
That's right. Carbon dioxide has polar bonds in it, but those don't actually result in a polar compound because of the symmetry that's in that compound. So, this dipole-dipole attraction drawn here, here's a molecule of HCl, here's another molecule of HCl. The partial positive charges are interacting with neighboring partial negative charges, and so forth. And this results in HCl having a strong attachment or strong affinity for its neighbors. All right, this dipole-dipole interactions. Now they're not very strong. See, they're only a fraction of the strength, well, not very strong compared to intra, I-N-T-R-A, molecular bonds. Like HCl, that bond there, that's a strong bond compared to, see it's about 1% as strong, or 99%, this interaction here is weak compared to the interaction or the intramolecular bonding between atoms in a molecule. Okay, so once again, covalent bond, strong, intermolecular attraction, weak, but the relative weakness is really what we're after here, because you can shift whether a compound is a gas or a liquid at room temperature simply by these intermolecular attractions. And here are some typical delta H bond energies. Delta H heat energy required to break this bond, HCl bond, and the heat energy required to vaporize HCl, so it's significantly lower. So now, we already knew what this slide says, but just a little reminder, if you take gas and it condenses to a liquid, or the liquid condenses to a solid, that actually releases energy. And the way we know that is because if I want to take a solid and melt it, I need to add energy to that solid. If I want to take that liquid and evaporate it, I need to add energy to that liquid. So the converse of that, gas condensing to a liquid, liquid freezing to a solid, those processes will release energy, or you need to remove energy from the system to allow that to occur. So here's some examples. Propane, 3 carbons and just hydrogens, no strong dipoles there. And so the dipole moment for this compound is very low. This molecule, dipole moment of 0.1. When I add an oxygen in there, you can see that the oxygen is kind of at the top, and I get asymmetric structure with oxygen pulling electron density away, because remember, oxygen is one of the electronegative hogs, right? And so the dipole moment is higher. Now, why do you think the dipole moment in this compound is even higher?
Well, I guess because the oxygen is more asymmetric, pulling it electron density away.
Yeah, we have oxygen all alone up here, and same thing with this one, even stronger with all the electron density being pulled to one end on acetonitrile here, the nitrogen there. All right, so our increasing polarity, our increasing dipole moment, and you also see an increase in the boiling point of the compound. Now, why does an increased polarity or increased dipole moment result in an increased boiling point of a compound?
I can't say that I caught that. I'm not sure.
Well, to boil something, you're heating up a liquid and turning it into a gas. Why do you have to heat up that liquid to make it turn to a gas?
I don't know. You just got to heat it up, right?
Yeah, but there's a reason why you have to heat it up. What you're doing when you heat up a liquid and if you're trying to convert it to a gas, is, so here is my molecule, and here's another molecule, some neighboring molecules. This is a liquid, and now I want these molecules to all jump away, fly away, right, and become gaseous. Well, for that to happen, any intermolecular interactions that might be occurring have to be overcome, right? It's these intermolecular interactions that are causing it to be a liquid, and if I want to overcome them, I have to add energy to overcome those intermolecular interactions.
Okay, I get that. That makes sense.
So that's why we see a higher boiling point with compounds that have a higher dipole moment, or that are more polar. All right, so we already mentioned the dipole-dipole interactions, right? But you can imagine that there's lots of types of interactions. One type of interaction is called what we call an ion-dipole. That would be an ion like sodium ion, for example, and something that has a dipole like water. In water, where's the partial? Water is polar, so that means we can draw the partial negative and partial positive sides or signs on this water molecule. Where would they occur? Where would the partial negative charge be?
Let's see. I guess the negative charge is where the electrons want to go. And do you have the periodic table there?
Let's bring this over here. Whoops. What's going on? There it is.
Okay, yeah, so oxygen is more electronegative. So the partial negative will be on the oxygen.
That's right. Partial negative here, a partial positive there. And that results in a dipole. And so an ion-dipole interaction can occur because ions have positive charges, and a dipole is going to have a negative charge. And that can result in an intermolecular interaction. It's not between molecules. This is kind of an ion, but it's still considered like an intermolecular interaction, right? You have an ion-dipole interaction. All right. A London force, we'll talk about that, or London dispersion forces. We'll talk about that in a bit, but in the future. But that's another type of intermolecular interaction that exists. All right, so we're going to go through these different intermolecular interactions and learn about them. Okay, good place to stop.